They're really interesting because mathematical expressions are innately related to languages, natural languages. Even the language which I'm speaking to you now can be described in terms of a generative grammar, in terms of primitives that words ultimately resolve to, and that structure of sentences can be represented in terms of combinations of others operations over these primitives in such a way that they can be evaluated and interpreted. I thought this was a cool idea because I thought when I read about languages and I read about compilers separately, I thought, wait a second, these are more intimately related than the current state of the art has actually led on to take advantage of. So what happened was Dr. Chomsky introduced the idea of grammars, generative grammars, and that made possible compilers. Compilers otherwise wouldn't have existed, and so the compiler field and programming language field took off and did their own thing, and the linguistics field did their own thing for decades, basically. Well, here we are today, and there's tons of programming languages. They're all rather mature. It's very easy. It's far more easy to build a mature programming language than it was in the 60s or so, than when it first came out. At the same time, linguistics has sort of itself done its own thing. I'm not near as much of a linguistics as I am a computer scientist, but I wanted to talk about how are linguistics, natural languages, related more intimately than they have currently been taken advantage of to programming languages. And so I wanted to go over, before I even start, what is the basic breakdown of compiler? When you write, int main void, return 0, open and close bracket for C or something, what does that get translated down to, and how does the compiler work? Why is the compiler so critical to basically every single computer scientist or programmer or hacker? No matter what you are, you use a compiler or an interpreter at some point in your life while you're developing code. And so I wanted to go over the phases. There's lexical and syntactical analysis. Before the compiler even starts to produce or emit code that the computer will execute, it has to read in and then interpret and give structure to the text that it was handed. In most cases, this is a single file at a time, 1, 2, 3, maybe I'll read a header, and while the compiler is reading that, it parses and interprets based upon a very strict syntax what that set of lexical tokens are. So you can write things like identifiers like int variable name, and that's like more than one character, and then equals something else, and it's generative. If you've ever seen the tree structure of a mathematical formula, like 3 plus something else equals something else, you know that you can type and rule over those items that are fully resolved based upon how their operations define their interaction, right? So maybe it's not 3 plus 5, it could be 3.0 plus 5, and it could be float plus integer, other things that can interact, strings and integers, whatever it is that the programmer defines. So that moves into interpretation and type checking. In terms of type checking, compilers do this thing that's really handy for users, where it's like, okay, look, while you're writing this program, you wrote a function where you added a 3, an integer, and a bool, and that's not well defined according to the rules that I had in context. Until you define that, it doesn't mean anything, so I'm going to reject this program. And that's what type checking and language rules are. And every language has its sort of superset above the basic set of natural rules that any person would use, right? And those are like language-specific rules. Like Python has its own sort of classes. C++ has multiple class inheritance. Scala has a different classing scheme and object scheme. In Java, everything's an object. And you can go on and on and on, talking about what's specific to a particular language. But at the ends of what you're getting at, you want to generate machine code, whether that's because the virtual machine that you're using spits it out while you're executing what you've given it, some kind of bytecode or something that resolves bytecode, or whether or not you've fully compiled it ahead of time, whether it be C or D or C++ or Rust or whatever. Ultimately, you have to get machine code, and that's what programming languages do. Programming languages are incredibly complicated and monstrous beasts of complexity and difficulty. If you've ever tried to build your own, you can appreciate this. So I'll just go over in natural languages. Whenever you're doing lexical and syntactic analysis, what we're actually talking about is syntactically, if I see a comma, or if I see a exclamation mark, or if I see a period or something, I interpret what I'm seeing differently. It augments my interpretation based upon a few scant characters that are littered around the text that I'm working over. But lexically, what I'm actually doing is I'm reading from front to back, and I'm scanning these tokens, and I'm producing a series of parse sequences based on lexical rules. In C, the easiest rule to think of is everything that is white space separates interpretation from that which is not, right? And that's really, really easy to remember, because if you see I, you can forget about the rest of this, and you can think of just I, and you can match that with a meaning sense interpretation in linguistics. So what I'm expressing is that programming languages, if you don't know the history behind them, in 1960, there was a doctor in the Navy. Her name was Admiral. I forgot just off the top of my head, but she's a famous computer scientist, and everybody said you can't make a compiler. You can't spit out machine code based upon just the structure of expressions. Grace Hopper, yes, that's who I'm talking about. That is exactly who I'm talking about. And you can't do that. It's too hard. Many computer scientists thought this. And when she did this, the rest of the world followed and said, "That's amazing! I can't believe you did it. This is so awesome!" And for just a short moment of science, linguistics and computer science kind of held hands, and it was like, "Oh, look, these grammars help us interpret what we're being given." In this case, grammars help you see. First, you tag what each spelling can be in terms of noun, verb, structures of sentence. Like what they're talking about here is I'm hitting S, or noun, or pronoun, verb. Different pieces of sentences alter the way that they're interpreted. And what I'm interested in is maybe what we can do with programming languages is we can actually weaken some of the invariants so that the computer does a little bit more work, but in such a way that it's still fast, while at the same time taking advantage of what we're giving it in such a way that it can disambiguate a little bit more flexibly. So what exactly does that mean? In terms of C++ and short deviation, when you handed a template class, you're saying, okay, resolve this class with a certain amount of ambiguity or vagaries, which are very specifically defined. I need certain functions, certain variables, whatever it is, and you plug them in with this other class, right? But maybe in terms of how you interpret something, you can be a little bit more flexible in terms of the way that natural languages works. So that what we're actually doing is we're asking, the idea we're exploring is can the computer do a little bit more work for us to make our job easier and more natural for us? And when we express something, the computer does more work in order to resolve what it's got to be closer to what we said. develop this interactive process where what we're saying is, okay, I'll hand you this piece of information, this thing that I say, the way that I speak about it, and the computer will resolve it in terms of the text that it's got, the structure of programs that it's got, and bring it closer to text, and it can be an interactive process, right? So what I've got is I've got interpretation, and I've got, what I'm trying to develop is this series of bijective relationships between compilers, which is this, and languages, which are these. And what I'm trying to say is, okay, look, wait a second, what if it's not just the grammar structure that is related to programs in such a way that you can define a language in such a way that it's like, okay, when I give you 3 plus something else, you interpret, you type check, you do all these operations to get a final result, and you translate according to whatever final language, machine code, bytecode, whatever it is that you finally compile down to, you translate it to that. Maybe instead of thinking of it just in terms of those generative grammars and the language rules that they write for a particular programming language, maybe there can be something a little bit more relaxed in terms of word and meaning sense interpretation and the ways that humans think of it. Like, how can we make the computer more amenable to human usage, human-computer interaction? So I kind of thought, in the lambda calculus we have, here's how we define functions that correspond to series of operations, right? And then when we resolve those operations according to other operations or values, we're applying them. And if we are defining a particular operation or a value, we're saying, okay, this variable is this one thing. If you've never seen this, what this actually says is, provided nothing, you can define a variable in the store such that it has type tau, given that x produces type tau in this context. And to read the other one is given type x has type tau sublet p, that's specifics for the context. This is the context of the store for all of the variables, all of anything in a given context that you're type checking in produces a type t. Tau has type t, or rather, x is related to that type this, and this is a lambda such that you can abstract what you're doing in such a way that tau p can be given a x such that it can produce a type tau of this. So now you can type check functions, and then after you define a function, this is like, okay, define a variable, define a function, define the application of that of any variable to a function, and it's done in such a way that mathematically you can define whether it be a variable that resolves to a function or a variable that resolves to a value. You can still mix them really flexibly, so you can pass around variables or functions. And this is really, really nice, especially when you get into more advanced programming. But what I thought was, okay, wait a second. Maybe in natural languages we have words, but we have more than one meaning sense definition in terms of a word. So when I say, any particular word, while I'm speaking to you, you won't suggest something that is totally and completely nonsensical and irrelevant unless you're making a pun or something, right? Because you're resolving the various meaning senses with the context, right? You're doing more than one operation in your brain. You're type checking, you're semantically evaluating just on the surface level, on the kind of structure that you have in that word, and the different things that it can be, And prepositional phrases, they're sort of like the syntactic salt of natural languages, right? So you're augmenting and you're altering nouns and subjects in such a way that they can be recycled. And subject, noun, verb is sort of like the reusable structure for any kind of natural languages. And it doesn't matter whether you're speaking Swahili or English. Subject, noun, verb can be remixed or reordered or salted language, they're always present. So I kind of thought that this was really good in terms of interpretation. How you finally resolve what you're being given can be more interactive than what was otherwise provided in terms of programming languages. So people that think about programming languages, what they do is they come up with programming languages and they're a little bit like a false dichotomy in the sense that, okay, whatever you write in this file, I'm going to read it, evaluate it, and then I'm going to produce some crap, and then I'm going to be done. But it doesn't have to be so dichotomous. So what I'm trying to get at is we can admit a little bit of divergence and allow the compiler to do a little bit more work for us while defining this language that we're going to work with and trying to bring this language closer to what humans actually use. So we can have multiple interpretations limited by syntax, context, and semantics. And in the sense that we reject something, what we'll actually say is we won't totally rule it out. We'll say, okay, look, if I were going to use this, I would have to have so-and-so rules in order to satisfy, some such and such constraints. Here's why I rejected this. This way, in an interactive sense, while I'm compiling something, I can say, oh, I see why you rejected that, instead of the compiler just spewing output like what you see in C++ or D or whatever language it is that you use. Syntactically, it's got to parse this, and the compilers aren't really always so kind. So I'm interested in the idea that compilers can not only be kind, but can more work in order to understand human. So I came up with an example, and I thought, okay, look, I wrote a black horse in red pajamas, black horse being the subject or I being the subject. And we thought that these two can diverge in the sense that, okay, if I had imagine a body of text before and a body of text after this example, right? And you can see, because you're human, you have the ability to reason, that there's more to the sentence, but that either the black horse can be wearing red pajamas or I can be wearing red pajamas, right? And that's pretty easy. That's a really simple example, but what we're actually talking about is an actual more general problem in natural language parsing and interpretation and evaluation that is shared with compilers. And what compilers do is they disambiguate. They say, okay, look, syntactically, semantically, we're going to completely and totally disambiguate the problem of issues here and here. And what I'm saying is okay, maybe instead of just totally disambiguating it, maybe the process of evaluation can be such that, okay, look, if black horse is going to wear red pajamas, why is this in a context that admits the black horse wearing red pajamas? And what I'm saying is we can use a little bit more information in terms of before and after, because sometimes when you're reading a book, it's not always clear what the subject is of a particular sentence until you read after it and have a little bit of information to be able to supplicate this interpretation, right? Right? Everybody knows when you're reading a book, sometimes there's a little bit of vagaries where the author weren't quite so sure why they were writing what they were trying to express, but you can still get to what they meant. In terms of how we interpret that, this actually means just maintaining more than one data structure in the sense of how we structure the internal manipulation of data items in the compiler. In this sense, it's just a tree. You can keep more than one tree and have this and this be different tree structures before and after in such a way that, well, if you admit this, then you interpret this according to this admittance. But if you admit this, then you interpret the afterword accordingly, right? And we can move on. What we're talking about is just the general interpretation of tension. So we're using the context of evaluation to disambiguate interpretation, or else raise an evaluation to spurn this to occur, right? So in the sense of natural languages, or in the interaction of this continuous compiler where we're just keeping it alive, we're supplicating it with information, the compiler can parse down later sentences to be able to alter what you gave it beforehand in the sense of, I'm writing this black horse in red pajamas or some such, right? And then by the time you're done with it, it can reliably restructure what you gave it into what you actually meant. So it doesn't matter so much that for a little bit of time, the compiler were wrong or unsure or something, so long as at the end it arrives at the final answer, because the human's always going to be like, oh, no, this is what I meant. But making the compiler be a little bit more difficult to work with is really, really not the answer. So then I wanted to say, okay, look, wait a second, maybe it's not just the structure of languages and how we interpret, separating interpretation from evaluation in terms of compilers, that is a kind of bijection that we're carrying over this series of bijections. What we actually mean is that beyond just the generative grammar of a natural language or of a compiler, there are whole suites of traits of languages that can be mapped over to a programming language. So if you're going to build a programming language, you can think about opcode selection. So in opcode selection, it doesn't matter whether you're using ARM or x86 or whatever. What you're actually doing is you have one tree of expressions on the left, and you have another tree of expressions on the right. And what you're trying to do is you're trying to match sub-expressions on the left to those and on the right. You're trying to discharge in sequences the structure of the tree in left and right in such a way that you reliably produce the same semantics, no matter which of those primitives you choose. And type and variable context can be mapped to your implicit local environment in a natural language. So when I begin to speak about an item and I mention a subject or a noun or a verb or whatever, what I'm actually doing is I'm introducing a verb. Those that use co-programmed proof development environments are really invariable, or really familiar with this, because what they're used to doing is saying intros in. I mean, introduce the variable called in that has the type this that is defined over this inductively, right? So, we want the computer to do a little bit more work in terms of the environment. Type inference can be related to semiotic structure recognition. So in terms of type inference, what we're actually asking the computer to do is given these concrete set of semantics, you have plus, minus, or plus float, minus float. In terms of a camel, it's absolutely, totally, completely disambiguated, and we want the computer to say, okay, look, there's a float on this side, there's a float on this side, or there's a this on this side, and this on this side, to just admit a little bit of more. Okay, look, you meant plus, but in case of whether or not you meant this kind of plus or this kind of plus, I evaluate them as until they disambiguate. This way, the computer can do a little bit more work to make sure that the expression that you gave it fully resolves, right? I'm a little bit more verbose. But interpretation evaluation, what we're actually doing is expression matching in its terms. And free and bound variables is a lot like articles of discussion. So in type introduction, whenever I introduce a new concept to you, like say I were to mention a subject, a noun, a verb, anything that is totally completely new to you, you'd have to ask a little bit about what that is. What you're doing whenever you're asking that is you're fully resolving what is defined over that, right? So maybe instead of just keeping such a small amount of primitives that are defined for a language, we can just admit a little bit more and then define it in terms of what's orthogonal in context to say whatever those nouns or subjects are. Then we want to say, okay, evaluation is not interpretation, but keep them separate such that evaluation leads to finally interpretation. That's the job of the compiler, right? But keeping multiple evaluations separate is really, really helpful to the user. And then build metadata for each parse tree fragment, right? So type implications, meaning sense interpretations, variable context influence, all those things that I just mentioned earlier, let the compiler do the work in terms of resolving to finally what the interpretation is, right? And then finally, type checking and language rules is identify, possible meanings and interpretations for each word based upon the context that they're given, right? So like if I give you something like a word in natural language that can resolve to something that has more than one meaning sense, we can resolve it fully. This is kind of like in C++ where you have an overloaded function, but you have a way to fully resolve it based upon what its signature is, right? So if you know the types of its parameters and what it should return, you know what it should resolve to, right? But it's more general in the sense of natural languages, and that we kind of like reuse that capability in more than one place. And then we want to also not just use it with the particulars of the signature, but also the context. Like in natural languages, I don't always mean to interpret something that is specific just to the discussion, because what's really helpful is I can actually ask you for how should I interpret this, and that's really helpful. Right now, I find that compilers support this idea of a dichotomy that shouldn't even be, which is whatever you write in the text, there's no ability to inquire on the part of the compiler for more information, more like to disambiguate. In the case of the discussion, whenever I'm talking to somebody, if I say something that's rather ambiguous or something, they're going to say, "What do you mean by this? X, Y, Z. Like if you meant this, then you mean this. If you meant this, then you mean this." But in the process of human discussion, what we're actually saying is, okay, look, I actually interpreted the rest of the body of your text and remembered that there was something unambiguous or something ambiguous, and I'm trying to disambiguate in order that I can supplicate my interpretation accordingly, in order that I can evaluate things correctly. So really what we're actually saying is that in natural languages, people actually keep this whole tree of parsing in such a way that whenever they're parsing something, they're listening to what somebody's saying, they parse something according to this way, but then possibly more than one, so they have more than one interpretation based upon a discussion that someone's giving. I think that's really helpful in terms of using a language. Like you imagine that Python, whenever Python, it's sort of like, everybody likes Python because it's a little bit more relaxed. But everyone probably agrees that I wish that Python didn't have, had a way to kind of not support a kind of dichotomy where we're like, look, I defined something and I gave it a 3, and that function shouldn't be defined with so and such type, but I wish you could just ask me for what to do with that, and to wait a little bit. So there's kind of like a set of reliability clauses that are kind of general across any language. So then I thought, well, natural languages have types in terms of their verbs, their nouns, their subjects, whatever kind of primitives that they're fully resolved to, all the way up to their tree of interpretation. When I'm talking about, I rode a horse and read pajamas. Pajamas and horses are each nouns with interpretation restrictions, right? And you might not, until you think about it in terms of like specifying, okay, this horse is defined for, blah, 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 blah. You wouldn't say it's defined for pajamas, right? So then the computer should probabilistically reject the interpretation. I rode a horse that was in red pajamas, and I rode the black horse, right, over the interpretation that I was in red pajamas while I rode that black horse, right? Because it's probably correct because I don't have an interpretation for that. And then to resolve the case where it's like, okay, look, why did you interpret it this way? Because what you're going to do in a regular discussion is you would find the case where that person interpreted it incorrectly. You would say, look, I'm not my horse doesn't wear pajamas. I don't have pajamas. My horses are not defined for pajamas. What you're actually doing is you're type checking natural language. When you get right down to the meat of it, what you want is you want to say, okay, look, you want to define the operations, you want to define the interactions of primitives that languages resolve down to. So rule out illegal meaning sense combinations with metadata about each word, right? And you can do that by whenever you introduce a new concept, the computer can do a little bit, also do work in terms of like looking that concept up from databases, while at the same time, possibly resolving a particular word in terms of what it read that mentioned or used, applied that word, right? In such a way that more than one application of the word, more than one application of the grammar that resolve a particular meaning sense definition or probabilistically okay. And we can use this to relax the constraints in terms of compilers. So I kind of thought, wait a second, maybe instead of, like writing semantics that were so concrete and difficult, we could come up with things that were like probabilistic in the sense that, okay, look, if I start to have success and I give the computer feedback in terms of like, this is what I want, probabilistically resolve these things and come up with variables in the background to track and retain, how to interpret how it should do things, right? And then I thought, well, type structure, recovery and inference and stuff, and application and type checking, all those operations can be probabilistic. And then I kind of thought, supposing you got that, regardless of how you got that, if you wanted to think about text, if you want to do like linguistic processing, whenever humans are thinking about natural language bodies of text, consider two, not just two, but like two or more. We're talking about like linear groups of natural language text. We're getting a little bit more mathematical. While we're in the process of interacting with this compiler, we're giving it additional pieces of information to resolve a body of text. What we're actually doing is we're starting with the origin, and we're editing that origin. We're creating differences. We're creating an algebra of a given body of text and the differences that we have, and we can reason in terms of those languages, whether it be computer languages that I construct or natural languages. We can reason about the differences between an origin or one of the changes or more than one of the changes between when we say, okay, fine, this is admitted, this right here is fine for so-and-so interpretation. So we have two bodies of text, one original and another edited, and while we're interacting with the computer, we're saying, okay, the computer is expressing back to us, okay, look, here are my two parts, my two interpretations for whether the horse is wearing red pajamas or you're wearing, the subject, is wearing red pajamas. And while you're giving it information, what it's actually doing is it's going down a trail. It's like resolving these sequences of differences, and it's actually comparing algebras of differences in the sense that, okay, this typing context, this variable context is defined for X and Y and Z, but then you introduce this different thing, right? And then you can write rules that type check according to the differences between what you've given the compiler while you're going through these phases, right? And my opinion is that there is an algebra in the sense that you can define things that are commutative, transitive, the regular abelian sense of operations can be defined in terms of textual algebra. Such an algebra between bodies of text and how you interpret them, or languages of variables, in just the same way that you can with numbers in terms of countability, like 0, 1, 2, 3, and they can be transitive, commutative, associative, and all those other properties in the same way that they can be about bodies of text. And that's hugely interesting in terms of natural language processing. Or rather, such an interactive compiler. And then I thought, like lazy kindness and then we're getting even more technical. When you talk about kindness, if you think about Coke, COQ, I'm sure you're familiar with it. When you talk about kindness, we're talking about groups of nouns or verbs, subjects of interpretation that are defined over a general set of operations, right? So when we say kindness, what we mean is that, okay, dog is the kind of animal that has 4 legs, just as much as horse or sheep or anything that has 4 legs we can define operations, classes of groups of bodies of text where it's like, okay, instead of maybe whenever I interpret something in terms of very, very strict semantics, in terms of this noun, this whatever, I can think of things in terms of what is the kind of item, the kind of noun, verb, any kind of primitive, such that it can satisfy a given item. And what I thought was, well, we had a set of kind of like a Google search for probabilistically resolving. We would say, well, it's probably a sheep that has 4 legs and 2 eyes, and this kind of iris and this kind of hair or something like that. And then only if you really stressed that item or didn't interact with it would it resolve incorrectly. And so those are my ideas in terms of linguistics and compilers. Here I am. You can contact me at my email address.
So, have you considered the problems of exponentially expanding ambiguities with this sort of thing?
Complexity, right? What are the problems of complexity in terms of interpretation and compilers? What I actually think is that oftentimes it's almost very infrequent that you can't resolve complexity issues with something like a caching or an indexing technique or an approximation, some such that can make it where it's effectively as good as another thing. So often, I don't often think about complexity or algorithms as being the limiting factor, especially when computation can move at something like 2 billion operations per second. What I think is that it mostly has to do with how can I make the job of the programmer more easy? How can I relax their constraints in such a way that they can speak to the machine and have the machine go, okay, I got what you meant, if you meant this, if you meant this, if you meant this, and ask, and making it more interactive, whereas right now it's kind of dichotomous. Not that it's not an issue. I think it is very probably an issue, but I haven't broke it out. So
You try to translate any of these ideas into software?
haven't yet, but I have several books. I have types of programming languages I've been reading, and compiler implementation in ML, which have different algorithms for things like maximal munch and opcode selection, this and that. And I've also looked at certain libraries. Syntaxnet by Google is really, really good for parsing natural languages. So I thought, maybe I could come up with like I could start with a probabilistic parser of natural languages and start from a different base in terms of compilers. But I haven't started to write anything, mostly because I don't have enough time.
Do you believe this problem can be reduced into a problem of detecting what behaviors a programmer would want versus wouldn't want? Is that like part of the probabilistic? It's most likely that they would want this. If it's undefined behavior, they probably don't want it.
Yeah. Very often, it's the case where it's like, okay, I can't import, so-and-so class. But what I actually mean is I'm trying to. It's a difficulty of expressing or marshalling knowledge between the human and the computer. Where what I'm getting at is the computer can do so much work that most of the time it's not working. And I think the majority of the issue is that that time isn't being used, and that I would like to relax the problem of leaving the problem at marshalling that knowledge. Because imagine that you write a particular extremely good whatever it is. Once you write it in that language, it's only good for the people that use that language. And things are constantly changing. And you know, I'm not really actually an advocate for HAXE, H-A-X-E, that language that compiles to any other language. What I am an advocate of is recognizing that I'm not interested in the particulars of your language, and I think it's actually kind of narcissistic to think that anybody would be so interested in somebody's language, like somebody would write a language and think that other people would flock. At this point, there are more than 20 languages knocking at my door, and I kind of don't think that I want to learn about the individual syntax craft of each language, right? I just want the subject of what I'm interested to get translated into that target, that, you know, translated into do this, you know? And I kind of think that a lot of other programs are the same way. Does anybody have any questions?
All right, thank you.